Hi, welcome to AB video 1.4a part 1. There will be a part 2 video, Introduction to Continuity. In this section, we're going to be looking at continuity, which is going to involve one-sided limits, which we've already talked about. So I do want to make one thing very clear. There's two types of continuity. There's continuity at a number, that is, at a particular x value, so like at x equals 3. Or it can be continuous on an interval, such as from -2 to 7, or from -infinity to infinity. But you would never just say, oh, that function is continuous. It's either continuous at a particular number, or it's continuous on a particular interval. So we're going to start with the book's definition of continuity at a number. Now they're going to call it continuity at a point. But really you'll notice it says if f is continuous. It doesn't say at a point. It says if it's continuous at c, which means when x equals c, at an x value. Now the way they're going to write it is three conditions need to be met. F of c needs to be defined, so there has to be a filled in dot at that location. The limit as x approaches c has to exist. The limit as x approaches c of f of x. And the first and the second parts must equal one another. They're going to mention continuity on an interval right now, but we're going to get to that actually quite later. A function is continuous on an open interval, a to b, and we'll come back to what happens if it's closed interval or half open, half closed. But for now, on an open interval, if it's continuous at each point in the interval. Again, that should be at every x value in the interval. A function that is continuous on the real number line, the entire real line, -infinity to infinity, is everywhere continuous. We'll never use those terms. We'll just say it's continuous for all real numbers. Okay, now I'm going to rewrite that, because if you look at item 2 here, it says the limit as x approaches c of f of x exists. Well, we just spent section 1.2 and section 1.3 determining that a two-sided limit, notice there's no plus or minus on that c right here, a two-sided limit only exists if the two one-sided limits exist. In other words, the limit as x approaches c only exists if the limit as x approaches c from the left of f of x equals the same real number as the limit as x approaches c from the right. So we can now rewrite this third condition and replace the limit as x approaches c of f of x by this expression right here, and we end up with what I call the trilogy. So we're just going to have one statement instead of three separate statements, and we're going to say that f of x is continuous at c if and only if these three things are equal. If f of c equals the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x. I would strongly suggest you write this one first, because you're so used to just looking at the two one-sided limits that you will forget that it also has to equal f of c. Okay? All right. Before we go any further, I do want to, so again, sorry, this is the same exact thing. And that's the trilogy that you're going to want to use whenever I say justify or show the work leading up to it, but it'll just be the word justify. If it says justify that the function f of x is continuous, for example, at 5, that would mean that you would have to show that f of 5 equals the limit as x approaches 5 from the left of f of x equals the limit as x approaches 5 from the right of f of x. And I do want you to notice that this is f of c, not f of x. Okay, so if they ask for continuity at x equals c, there has to be a c here, a c here, and a c right there. All right, I do want to talk about the three types of discontinuity, and basically what we're going to be looking at is anywhere on the graph that you need to lift your pencil off the paper in order to continue drawing the graph. So one of the most common is what you guys would call a hole, which is a point discontinuity, and we're going to look at examples of all three. Another type of discontinuity happens when you have a jump discontinuity, and we've actually already seen that with piece functions, how the limit as x approaches, say, 3 from the left is one number, but the limit as x approaches 3 from another, from the other side, the right side, is a totally different number. Sorry about that. The third type is an infinite discontinuity, and that's, of course, a vertical asymptote. But in all three cases, you would have to lift your pencil off the paper to keep drawing. So here's an example of each. Here's a point discontinuity. Here's a jump discontinuity. The graph jumps from one height to another. And here's an infinite discontinuity where the limit as x approaches c from the right or from the left is positive or negative infinity. Okay, now just to give you an idea of the kind of function this would look like, it is a line with a hole. It would actually start out looking like a rational function. The numerator would factor, and that factor would occur also in the denominator. So you got to be careful you don't just look at the denominator and go, oh, there's a vertical asymptote at x equals 2. That would only be true if the factor x minus 2 did not also exist in the numerator. But if the same factor occurs in the numerator and denominator, yes, they cancel out, but it causes a discontinuity at 2, right there. And then how do you find the y-coordinate? You take that 2 and plug it into what's left, which, by the way, is a line, f of x equals x plus 1. A jump discontinuity most likely would come from a piece function where it equals one thing on the left of 2, a different thing on the right of 2, and those two heights aren't equal, and you've seen those. And of course, an infinite discontinuity would be a vertical asymptote. And that, of course, would be when the factor in the denominator does not also occur in the numerator. Okay? So those are the three kinds of discontinuities. I do want to just look at this one up here to show you that the limit as x approaches 2 from the left. So as I get closer and closer to 2 from the left, it is going to positive infinity. However, when you approach 2 from the right side of 2, you are going down to negative infinity. Now what happens is the two-sided limit for that one would simply not exist. If they were both going up to infinity on either side of 2, we would say that the limit as x approaches 2 from the left is infinity. The limit as x approaches 2 from the right is infinity, which really means neither exists because they have to equal a real number. But here, because they are approaching the same concept, I'll say, because it's not a number, you could write infinity, which means you could also write does not exist. This is, I want, as I keep emphasizing, a more descriptive answer than this is. Okay? And that's the end of video 1.4a, part 1.